Chandra Program Scientist at NASA headquarters. Next, Ezekiel Traister, astrophysicist at the University of Hawaii at Manoa. Next, Kevin Shavinsky, astrophysicist at Yale University. Next, Priya Natarajan, professor at Yale University. And Mitchell Begelman, professor at the University of Colorado, Boulder. Each speaker will give a short presentation, and then we'll move to question and answer with the audience and for those joining by phone. For those of you joining us online, you can find out more information about today's briefing, including related multimedia materials, at www.nasa.gov/Chandra. A reminder that Dr. Traister and Dr. Shavinsky will participate in a NASA web chat on these findings and black holes generally at 3 p.m. today, and you can find the link to that chat room on the nasa.gov homepage. And with that, I'll hand it over to Wilt Sanders.
Thanks, Trent. The Chandra X-ray Observatory is the world's most powerful X-ray telescope. It has 8 times the angular resolution and can detect sources more than 20 times fainter than any previous X-ray telescope. The Chandra X-ray Observatory is part of NASA's fleet of great observatories, which also includes the Hubble Space Telescope, the Spitzer Space Telescope, and the now deorbited Compton Gamma Ray Observatory. Chandra's superb imaging and sensitivity allows scientists from around the world to obtain X-ray images of exotic high-energy phenomena and environments to help us understand the origin, evolution, and structure of the universe. Over a decade ago, a group of distinguished scientists sat on this stage. This group included Nobel Prize winner Riccardo Giacconi, and to announce the results from the first Chandra deep fields. At the time, these were the deepest X-ray images ever obtained, and they amazed us with new and exciting discoveries about the early universe. Now, we're here again to talk about the next generation of the Chandra deep fields. The image discussed today results from more than 4 million seconds of Chandra observing time, which is more than 4 times as much as the original deep fields contained. So it's appropriate that this panel also includes the next generation of scientists who will lead X-ray astrophysics in the coming years. All of them are already distinguished scientists, and 2 are Einstein Fellows, which is a NASA program to help support some of the best scientists in their early career stages. Without any further delay, then, let me give the floor to Ezekiel Traister to discuss today's remarkable new findings.
Thank you. We found evidence for the existence of a very large number of massive black holes in the early universe when it was less than 1 billion years old. We performed this study in the Chandra Deep Field South, and as we can see in the following animation, this is a very small part of the sky. We now see a big part, including the Orion Nebula, the Orion constellation for reference, and now we are zooming in a region about 1/3 of the size of the full moon that concentrates the deepest optical and near-infrared observations performed by the Hubble Space Telescope, and more importantly for our work, the deepest Chandra observations of the X-ray sky. This field was observed for 45 days by Chandra, and about 200 galaxies in the first billion years after the Big Bang were detected. Zooming in into a smaller region, we now see a few of these galaxies, and it's important to note that none of these galaxies were detected in X-rays. However, when we use a technique called X-ray stacking, which is basically summing the X-ray emission from multi-sources, even if it was undetected, we get a very significant signal, like the one we see now in the next image. This detection of X-rays from these galaxies is very important because it tells us that there are supermassive black holes growing in them, as we can see in the next image. In fact, we concluded that about and at least 30% of these galaxies in the early universe contain growing supermassive black holes. As we can see in the next image, this black hole is completely surrounded by large amounts of gas and dust, and only the very high energy X-rays manage to break through and go through this obscuring material. It's in the same way that when you go to a doctor's office, you perform X-rays that go through your skin, and you can study, you perform medical studies. This also explains why it took so long to detect these signatures. In fact, it took 7 years to detect right now the first signatures of growing supermassive black holes into these galaxies, and it took a combination of two of the NASA great observatories like Hubble and Chandra. Now, we knew about the existence of other supermassive black holes in the early universe, the so-called quasars, but those represent the last stage of the evolution. They already did most of the growth. The sources that we found out that these black holes are the progenitors of the large supermassive black holes that we see today in the nearest galaxies. We were, of course, very excited to find this. We were not expecting to find this X-ray signal from the early universe, and we were even more surprised to find that they're all heavily obscure. And now I'll leave you with my colleague, Dr. Shavinsky, who's going to say more about the implications of these results.
Thank you very much. So as Ezekiel Traister showed us, what we've seen are baby black holes in very young galaxies at the dawn of the universe. As we'll see in the next figure, these black holes are feeding on material, gas, at the centers of these galaxies, and they'll continue to grow through their adolescence to adulthood. They may also merge with black holes from other galaxies as their hosts merge, and they may end up accumulating 100 or even 1,000 times the mass that they have in the early universe until they end up at the centers of nearby galaxies. Now, as we'll see in the next image, this is the center of our own Milky Way. Galaxies in the nearby universe contain very massive black holes at their center. In the case of our own Milky Way, the black hole weighs about 4 million times as much as our Sun. But there are even larger monsters lurking at the centers of giant elliptical galaxies such as M87, which may be as much as 1 billion times the mass of the Sun. Now, one of the remarkable discoveries in astrophysics is that not only do galaxies contain black holes at the center, but galaxies and black holes seem to grow together. Big galaxies have big black holes at their center. Small galaxies have small black holes at their center. We believe that they have this a fundamental symbiotic relationship between the two. The growth of one regulates the growth of the other in a kind of feedback loop. What our observations of galaxies in the very early universe, as the next animation will show, tells us is that these very early young galaxies at the dawn of the universe and their growing baby black holes already had some sort of deep fundamental connection between them. They were already growing together, and so this chicken and egg problem of what was there first, the galaxy or the black hole, has been pushed all the way to the edge of the universe. Previous studies of black holes in the early universe were limited to quasars. Quasars contain black holes already as massive as 1 billion solar masses, so already fully grown up. So what these baby black holes tell us is that we can now move much, much closer to the moment of birth and really understand where both galaxies and their supermassive black holes really come from. Now, this discovery was enabled by two of NASA's great observatories, Chandra and Hubble. They make an excellent team, and we've only just scratched the surface of the first billion years of the universe with their help. And there are great prospects for further discoveries in the coming years with the help of these two great space observatories. I now hand over to my colleague, Professor Natarajan, to discuss some of the theoretical implications of this result.
Thank you. These results have very important and significant theoretical implications for some of the key challenging problems in cosmology today, one of which pertains to our understanding of how the first ever black holes formed in the universe. So it is pretty clear that you first make small seed black holes in the early universe, and over cosmic time, by swallowing gas in their vicinity, they grow. However, how precisely you form seed black holes is an open-ended question. And there are two schools of thought, theoretically speaking, on the matter. So the first model suggests that seed black holes essentially form as the end states of the first stars that form in the universe. So seeds that form in this fashion roughly range in mass from a few hundred times the mass of the sun to perhaps 1,000 times the mass of the sun. They're relatively light. The other way to make seed black holes involves the direct collapse of gas disks, which makes very, very massive seeds. And these seeds can range in mass from about 10,000 times the mass of the sun to about 1,000,000 times the mass of the sun. Starting off with these very massive seed black holes comes in rather handy to solve some other observational puzzles. So we proposed a model a few years ago that did argue for very early formation of extremely massive seed black holes. The other interesting feature of those models was an intimate link was construed between the formation of the black hole and the assembly of the stars in that galaxy, initially, from when the seed originally forms. What is very exciting is that these observational data seem to suggest that that is indeed the case, that very, very early in the universe, less than 1 billion years after the Big Bang, this early population of black holes, there appears to be an intimate connection between the properties of these growing black holes and the galaxies in which they sit. Of course, a lot more data is needed before we can adjudicate between these two models. However, what is very exciting is that now there is observational data for theoretical modelers to constrain scenarios. So quasars that are scant have provided information about the life cycle of black holes in just about the first billion years or so. And quasars are rare. Therefore, finding this entire population of obscured black holes opens up a whole new window into our understanding of how the first black holes ever formed. So this isn't a baby step forward. In fact, it's a really large leap towards our understanding of how baby black holes formed. The second science question upon which this has huge bearing is our understanding of the very, very early universe. In particular, the phenomenon of reionization of the universe. Right after the Big Bang, the universe basically consisted of hot plasma. And as the universe expanded, and looking at this graphic, you can see a very nice artist's impression of how this process might happen. You needed sources, the first sources, stars or accreting black holes, to actually turn on in the universe, and radiation from those sources was needed to open up and clear out this cosmic fog. So prior to that, we expect the universe to be in this stage called the Dark Ages. Of course, the question has been, which sources, what kinds of objects actually produce the light that can ionize hydrogen and reionize the universe? So from the fact that this entire population looks extremely obscured, it's very, very clear that these first black holes are quite unlikely to produce the light that removed this dense fog. However, what is very interesting is our finding also suggests that the stars and the black hole grow in tandem. Therefore, somehow, light escapes from the stars that form in these baby galaxies. However, no light escapes from these very obscured, copiously growing black holes.
Thank you, Priya. Now that we have heard from the team that's responsible for these results, I'd like to turn to an outside expert to offer some additional analysis and commentary and context. Mitch?
Thank you. Well, this result is really several breakthroughs rolled into one. It's the first time that we've caught black holes in the act of vigorously growing in the early universe. Now, we know that we've known for some time that there were black holes around quite early in the universe because we see quasars, which are absolutely gigantic black holes that somehow managed to grow to 1 billion times the mass of the sun less than 1 billion years after the Big Bang. But these are extremely rare objects, and we never saw, until now, the smaller black holes that must have existed before these quasars could have formed. And now we're seeing the first direct evidence for these smaller black holes. Not all of these black holes are going to become quasars. Most of them are going to become the ordinary massive black holes that are in the centers of every galaxy, including our own Milky Way galaxy, as you saw a few minutes ago. And so we're really seeing a process that is not kind of an extreme process that occurs only very occasionally in the universe, but we're seeing a natural part of the development of galaxies and all the structure we see around us today. And so the first breakthrough is that this is the first time we really are pinpointing when these black holes were really forming and growing. The second breakthrough is that we're getting the first clues as to how these black holes grew. When people thought about the growth of these black holes, they suspected that they had to grow fairly late in the game of galaxy formation, because when black holes grow, they liberate a tremendous amount of energy. As matter falls into them, as they swallow matter, they just produce a huge amount of energy, which is believed to have an explosive effect on the environments. Now, Dr. Chavinsky talked a few minutes ago about this feedback loop, which we think regulates the growth of galaxies and black holes together. But we know roughly when this feedback must have occurred, and if black holes grew explosively too early in the universe, that wouldn't agree with our observations. But what these new results show is that black holes were protected. They were enshrouded in a cocoon of dust, which dampened the effect that they had on their surroundings. And so, this feedback probably did occur, but it occurred in a much more gradual fashion. And so we now see that these black holes could have grown quite early without having a dramatic and unobserved effect on the universe. The third breakthrough I see in these results is it tells us something about the value of these great observatories. Nobody expected, nobody designed the Chandra Observatory to discover black holes. It took the research that was done over the last decade with Chandra for people to begin to realize that you could, by observing very deeply in the universe, that you could piece together some of the very early history of black hole growth. And so it shows the value of having a satellite up there that exists for a long time and is able to evolve and is able to be to have its mission adjusted so that people can do creative new things as the opportunity arises. And so, in particular, having Chandra there at the same time as Hubble, we see that there's been a tremendous symbiosis between these two observatories, which have really allowed a discovery that was completely unforeseen until very recently. So going forward, I see that these observatories continuing to operate will take deeper and deeper images, and probably over the next few years we'll see our picture of the early evolution of black holes and their relationship to galaxy formation fill in, and we'll get a greater understanding of these processes.
Great, thank you very much, Mitch. We'll move on to the question and answer session now. Just a reminder for those of you in the audience, we have a couple of microphones, so just wait until it gets to you. For everyone here and by phone, just please remember to introduce yourself and your affiliation before asking a question, and please try to direct a question to a specific panelist. And if you can signal the operator, if you're on the phone, that you have a question by pushing the *1 keys. So let me start and see if there are any questions here in the audience. Okay, well, let me take podium privilege here, because I did have a question for the panelists. And Mitch spoke a little bit about upcoming research, or what you see the potential for being as follow-on research in the next few years. But I'd ask the panelists what you're most interested and excited about this finding, and where you see people taking it from here.
Okay, should I start? So, yeah, so the most exciting part is to find this amount. If you extrapolate from what we knew, and people did this, they tried to estimate how much growth there was at the early epochs based on what we knew closer to us. And turns out the answer was about 100 times shorter than what we actually measured. So we found about 100 times more black hole growth in the early universe than what you get if you extrapolate from closer to us, from what we knew before. So that was very exciting. Also, I don't think people expect most of these sources to be heavily obscure. So that was very exciting as well. And I think in the future, and this was, as I think Dr. Natarajan said, this is a big step, not a baby step, in getting closer to understand where the black holes form and when they were created and when they started. So I think that was very exciting.
So I think the most exciting next step to take, of course, is to tackle this question that Professor Natarajan discussed, which is, where did the first seed black holes come from? And it may be possible by combining both Hubble and Chandra and taking even larger images of the very early universe, we may be able to start up picking up differences in the properties and the numbers of black holes in the very early universe that might deliver some clues as to which mechanism the death of the first stars or the collapse of these pregalactic disks really formed the original seeds to these baby black holes that we're seeing.
So I think personally it's very, very exciting to finally have some observational data points for us theorists who've been playing with these models for a very long time. I think what is very exciting is till now the only data point we had to calibrate our models and to hone our understanding were from data points from these very rare quasars, roughly from when the universe was about 2 gigayears old. So pushing that frontier and getting more data so that we can push back the wall to see how much earlier these objects are already in place or are assembling is going to be very, very important to really understand how the first black holes formed.
Just a follow-up question on that. If you were to estimate future research, how far back do you think we can get based on what's there now? If you're looking back at the timeline of the universe, with observations with Chandra and Hubble, as you said, working in conjunction together, how close can we get to the almost birth dates of some of these baby black holes?
Well, I think the models for making these seed black holes, in particular the massive seeding models, really start quite early on in the universe. But we're pretty close to that wall. So I would say that we could plausibly push another couple 100 million years or so. Would you say, Ezekiel and Kevin, would you agree?
I was going to supplement your answer. From the observational point of view, I think it's feasible. It's very ambitious, but if we spend a few years, not contiguous, of course, observing with Hubble and Chandra, we should be able to push it a few million years, and that's when things get really interesting, because that's when the models really start to separate, and we are able to constrain these models and understand how the first black hole formed.
Yeah, so I think just exactly how much further back we can go with Hubble and Chandra kind of depends on what mechanism was at work, what these seed populations were. Because these baby black holes, they grow very rapidly, and but they have to reach a certain size before they become bright enough to be so we can pick them up with Chandra.
I know there are a lot of people joining us online and watching from the public today, and there's a core concept that I want to make sure people understand, because I know it'll be of interest, particularly for the 3 p.m. Eastern Time web chat today, and that's reionization. So for those of us who aren't quite familiar with what this process would have been like from the Big Bang up to the point that you're talking about what these black holes may have affected, maybe we'll start with Priya. Could you just kind of explain the concept of reionization for us?
Sure. So reionization refers to the particular phenomenon that occurs in the slightly late universe when the universe was essentially opaque to radiation and then suddenly starts becoming transparent to light. So right after the Big Bang, the universe is filled with plasma and it's transparent to radiation. Hydrogen recombines and you form neutral hydrogen that forms this fog, and the universe becomes opaque to all radiation. And eventually, when the first sources of light form in the universe, be it growing black holes or stars, should start opening up this fog and should start destroying this fog. And so that process is called reionization. We expect it to be not instantaneous, but rather a gradual process. And the details of that process really depend first on whether stars form first or black holes, accreting black holes form first, or they may occur concurrently, coevally. So the sequence of how things happen in the universe are very critical to our understanding of how the process of reionization occurs. So it's, if you will, it is a lifting of the veil of the dark ages of the universe and bringing sort of transparency.
Thank you very much. Let me do a last check in the audience and by phone for any questions that we may have. Okay, well, with that, we will close today's event, and I just want to thank our panelists for joining us today, and for those of you online watching. Again, you can find out more information about today's results and assorted multimedia at www.nasa.gov/Chandra. Thank you all for your time. Have a good day.